Okay, I'm going to go ahead and get us started with today's SAD 2020 talk. Today, we're delighted to welcome Vanessa da Silva Brum Bastos from the University of St. Andrews, who will be talking about movement analytics using geospatial temporal data to understand behavior. Dr. Brum Bastos received her PhD in geography from the University of St. Andrews. In 2019, she was a postdoctoral research associate at Arizona State University in the US. And since January 2020, she's been back at the University of St. Andrews as a postdoctoral fellow at the Bell Edwards Geographic Data Institute. Her research focuses on the development and implementation of context-aware movement analysis to further understand behavior from movement data. More specifically, she is interested in combining movement data with environmental and socioeconomic variables to understand how different factors can influence human mobility and wildlife behavior. This knowledge is critical for planning egalitarian, sustainable transportation systems, as well as designing biodiversity conservation plans. It's really our pleasure to welcome you today, Vanessa. And so just for the audience, we've got a nice, healthy audience today. What we're going to do is allow Vanessa to talk for about 40 minutes. And then we'll have all questions and discussion after her talk. So what you could do would be to make sure you're dropping those questions and comments into that Q&A box at the bottom of your screen so that we've got lots of seeds for discussion after she's done. And with that, I will turn the floor over to you, Vanessa.
Thank you, Rachel. I'm just going to share my screen because for some reason the mouse just disappeared. Okay, found it. Share. Let's try starting the presentation. Can you see my slides now on full screen? Good. Okay, so thanks everyone for coming to my talk. And what I will try today is basically tell you a story where my research fits in and why I do it, and some of the studies I've been working on as well on movement analytics. So the story I'm going to tell you basically starts with movement ecology. So movement ecology is focused on looking at the movement of wildlife, the movement of animals, and trying to understand their behavior from that perspective, the movement perspective. So at its beginnings, movement ecology would focus on like getting their data, their tracks from things like footprints, and it was kind of a data poor science in that sense, because it was data that was really hard to get. You would have to always go to the field work and like track just footprints, also footprints and track as well, like sometimes cats or what or any other like material or trace of a potential trajectory of a given species or animal. But then what happens like in the last 15, maybe 20 years is that with the cheapening of like GPS devices, locational devices and technologies, movement ecology became a data-rich science. And specifically here we have this paper by Francesca Cagnati about how animal ecology meets the GPS technology, GPS-based telemetry, and how it creates a whole new set of opportunities for research. Because now the data that was really hard to obtain, it's more easily obtained in the sense that you can retrieve the location and time and space of animals, like using GPS collars like this one here, or smaller GPS trackers for animals that are smaller, like birds, for example. And even nowadays, they have like a global repository of movement data on animals that's called MoveBank. It's really nice. If you want to go and check, there are like loads of data available there. And here you have a synthetic ear showing the movement of like all the data sets they have there for a year, the flow of like different species. So you have this change in movement ecology, you have more data coming in, new opportunities, but also new challenges. And at the same time that movement ecology is becoming a data-rich science, we also have this change happening in human mobility studies, because now our only data source is not just like surveys, but we also have locational data from like diverse sources, like tweets that are tagged, Facebook locational data. We have timeline history from Google. We have location-based service from which you can give in certain possibilities like get data. You also have studies where you can use pocket GPS devices to track people and then like study their mobility patterns. So up to this point in this context, we know that like we have the locational data, which means we can locate in space and time individuals for human mobility studies and for wildlife studies in terms of movement. However, when we talk about movement analytics, we are not only talking about the locational aspect in space and time. When we think about movement analytics, we're trying to understand movement in a way that we also need, particularly in the last like 10 years here, consider context. And what do I mean by that? When we talk about movement data, we are mostly talking about trajectories, and that means like polylines in a three-dimensional space, where here you have like the geographic space at the bottom and time in the vertical axis. In an example of like some trajectories represented here. So these polylines, they can be three-dimensional, so like space, time, they can be four-dimensional considering altitude, but they actually can have so many attributes and dimensions that as many as you want. But when you consider just the spatial temporal aspect of them, we are able with movement analytics to know where individuals are going and when they are going. But the interesting part of the game comes when we add context to that information, and then we start to find and look for patterns that can tell us like something more about behavior. Examples of this is like matching trajectories with vegetation, pollution, seasonality, and air temperature. For example, if I have trajectories from an animal in the mountains, and I know when the vegetation like changes its state, and I can relate this change to different patterns or frequency of movement, and then that tells me something about the behavior of that animal, for example. Or if I match human trajectories with data on weather, on rainfall or wind, that can tell me how people change their transportation mode choices according to the weather, for example. So, and that's why the context part is, in my opinion here, and it's a biased opinion, the most interesting part of this whole movement analytics game. So, and well, of course, as I find it the most interesting part, my research actually focused on context-aware movement analytics, which has this core idea that you can match trajectories with contextual information to better understand and predict behavior. Here, I'm showing like a trajectory in a space-time cube where you have geographic space at the bottom and then time in the vertical axis. So here is just like a hypothetical environmental variable that could be like rainfall or could be vegetation. And basically we are annotating this trajectory with data from these layers. So we are integrating context into movement data. And now what I will do is like, I will give you examples of like 2 research projects I've been working on that relate with this idea of context-aware movement analytics and understanding behavior. So the first one is the project I'm currently working on that's using geomagnetic data from tags for analysis of migration. So the whole idea here, well, first of all, I need to tell you that most of you know, but the Earth has a magnetic field, and this field has like geomagnetic lines that go from basically pole to pole. The field is stronger in the poles and weaker around the equator, and it ranges from like 60 nanotesla in the poles to around 25 around the equator. And this field, the geomagnetic field, it can be characterized by different properties. Like the horizontal, this here in blue is the same geomagnetic field line that's represented here. So this geomagnetic field line has components like the northward component or X, the Y component, the horizontal component, and the down component, and parameters like declination and inclination. And this different parameters create a certain kind of map that we are not used to see here. And this is the map of the main field total intensity. As you can see here, we have like the stronger lines at the extremes in the pole. But this system here is very different from the geographic system that we usually use. But you still can use it for locational purpose, because if you think about the intensity of the field, and I'm not even talking about the other parameters that I told you the field has, you can differentiate being located at this area here from being located at the equator. Also, another important thing to say is that this field is not like static, like I'm showing here. There is some different sources of variation at like a higher temporal resolution and lower temporal resolution, which means this field can vary from a scale within hours to like centuries. But here, when we talk about using this information to study wildlife behavior, we are interested in variations at like hour to day to month like scale. So the Earth has this field, and its field has like many different properties. It varies with seasons and with days. And the question here is like, in ornithology, there has been this long-standing question on whether birds can sense somehow this field and then use this field to navigate. And the issue with that, like, there hasn't been any like definitive proof that they can or they cannot. There has been like a lot of studies in terms of trying to prove that or disprove that, but most of them were restrained to a really small number of individuals, and they were mostly like lab-based and were not fully able to reproduce the conditions that birds of different species would encounter in the wilderness when like migrating, for example, because the main idea is that some birds would be then capable of using that magnetic field lines to migrate long distances. How? Well, there are like multiple hypotheses on like some birds may have an enzyme that allow them to see these geomagnetic lines and they can follow them. Other birds might have some sort of mineral in their beak that allows them to sense changes in the field and use it for direction. But the point here is like, if we want to try and then prove or disprove that that's happening, we need a way to measure the magnetic field at the same point in space and time as these birds or bird are then experiencing it. So there are some ways to measure the geomagnetic field, and mostly like we have the most like robust ways nowadays are like using observatories and using satellite data. there is a network around the world called the Intermagnet network of geomagnetic observatories. And there are like satellites like the Swarm mission that are solely designated to measure the geomagnetic field and its components. All this, like both observatories and satellites, have been through a very extremely thorough process of like calibration. Why? Because this equipment, like these magnetometers that are measuring the field, they can be influenced and biased by like temperature, electrical components. So you need a very, very thorough process to calibrate them. Another way recently that has been used to measure this, the field, now thinking about like movement studies, is putting 3-axial magnetometers on board of the tags that we use to monitor, to track birds when they're flying. So here I have a picture of like these tags. They're basically like about, I had one here, but I don't. They're basically about like this size. They're very, very small. And you attach it to the back of the bird, and they have like a 3-axial magnetometer inside. This kind of like tag has been successfully used in studies by Hannah Williams, for example, to look at different like to identify from this data the posture, changes in postures of birds. But it hasn't yet been used to look at the geomagnetic field around these birds when they are migrating. And we believe that one of the main reasons for that is that there is no like calibration procedure that has been established for that. And we don't know how much we can actually trust these values. So we decided that we would then try to create this calibration procedure, because we really want to know how birds migrate and if they use the geomagnetic field or not. And we want to look at multiple species, so we really need these tags to be calibrated, accurate, and ready for use. So the first thing that I need to tell you when it comes to calibration is that the geomagnetic field can be represented by something that we call the M-sphere. And here, please totally forget the geographic space. This is not geographic space. It's more like a geomagnetic space where you have remember the vertical axis I told you about? That the geomagnetic field, like the geomagnetic field has a vertical component, a horizontal component that's X and Y. Here is the same representation, but basically what I'm trying to show here is that when you have a geomagnetic field under calm situations, which means there is no variation and it's being measured ideally without any interference, what we would expect from the data measured by that tags is like that it would fit on a surface of a sphere, like ideally if the data was accurate and free from interference. However, data world is not always pretty, is it? So what we actually get is some sort of like distorted ellipsoid that has something to do with the sphere, but it's not really the data we want. And we need to find ways to calibrate these distortions here to go back to our pretty sphere where we actually have our data. So that's one of the interference we are working on. And another reason to perform the calibration is that when we talk about the 3-axial magnetometer on board of that tags, we actually have 3 independent silicon etched magnetometers, one for each axis of the geomagnetic field that I told you about, so X, Y, and Z. And as these components are in different positions and they will be receiving interference from temperature and other variables in different ways. We need to perform this calibration by axis then. So here I will show you like the first effect is these 3 mag on board of tags, they are extremely affected by temperature effects. So here's an example of some measurements I perform in my yard. Basically, I put one of these tags in the freezer, and then I took it outside and I let it sitting and measuring the field. And whilst the temperature was basically increasing. So here you have the temperature in gray, and then the strength of the geomagnetic field that I was measuring. And you can see that there is a relationship, because you see an apparent like increase in the strength of the field, but actually it's pure and solely due to change in temperature. So we need to deal with like temperature effects when using this data, and this is especially important if we're talking about using this data to study like bird migration, because some birds will fly so high that there will be a considerable like change in temperature. And if you're not aware of that and calibrate for that, you might think that there was a change in the magnetic field, but actually nothing happened, just temperature. Another thing that we need to calibrate for, and this is more like well-known in the community, is the what we call the hard and soft iron effects. Basically, in generally speaking, the hard iron effect or hard iron vector that I show here is the difference between the center of that blue sphere I showed you here and this ellipsoid. So basically the hard iron effect is the vector that moved and shifted the center of this data from here to here, and we need to find it to subtract it and correct the data. And the hard iron effect is usually caused by like metallic components that you have in the tag. It's like an addition to the field, geomagnetic field that would be there. The soft iron effect is the one responsible for causing this distortion here. So it distorts this like pretty perfect sphere to this somewhat like ellipsoidal like shape. And it's caused by additional fields that you have like from the tag, and they will deform and misshape the field that you're measuring. So it's another thing you need to calibrate for. The other thing is what we call the magnitude effect, because when you measure with these tags, you need to find how much of the units they are measuring actually correspond to the real units of the magnetic field. And here is an example of a test we performed that like you have to kind of blow up the measurements to have this sphere. And the fourth one is what we call the coordinate system. The idea here is like you have this tag flying on the back of the bird, as you can see on the slides. And what happens is that you went measuring the components of the magnetic field, not really in the magnetic, the Earth-based like coordinate system or magnetic, because the total field here will be accurately measured, but the components will vary according to the position like of the bird or individual. So we need to move these measurements from a dynamic body-based coordinate system to the GPS coordinate system, and then to the Earth-based coordinate system, which is the one we use to measure geomagnetic, the geomagnetic field. The importance of this part comes from the idea that like maybe some birds or like a bird or an individual will be responding, for example, to the horizontal component of the field, which is calculated by a vectorial sum of x and y, but not to the total field, which is what we get only if we don't calibrate for the coordinate system. So after knowing all these problems with measuring it, we decided to try to create a calibration protocol that could be used by ecologists when they are attaching this kind of these tags to animals in the field work. So considering the errors that I told you about, we knew that we need to create like a temperature correction, hard, soft iron magnitude, and then a coordinate system rotation. And now I will explain you some like of the experiments we create to try and calibrate for that. And this is an ongoing work, so suggestions are also welcome. So for the first correction, the temperature correction, what the idea we had is like, okay, something that I can do with these tags that ecologists will also able to do, I can put it in the freezer, wait for 72 hours, then take it outside on a geomagnetically calm day, which means there is no storm. The field is like stable, not varying a lot. And then I know that in such day, any variation that I see in the geomagnetic field measured by this tag will then relate to temperature variation. Here is just the tag is inside this ice bucket, but what I did is like I removed the tag from the freezer, put it outside sitting in my garden without the ice, and just let it measure for like 60 minutes. So here you can see that as the temperature increases and the tag starts to warm up, there is like a difference in the measured field that has nothing to do with variation, but just like bias from temperature difference. And then what we do here is like we can collect this data, and then using some like algorithms and algebraic maths, we can use matrices to correct it and then get to what the data would be without the temperature variation. And then here I show you like the components in X, Y, and Z, where in blue you have what was measured due to the temperature variation, and in red, the corrected data. So that was the first strategy to deal with the temperature correction. The second experiment in strategy that we created for, this is for hard iron and soft iron correction, was we get this tag, and this also we learned with one of our co-authors, Hannah Williams, and you rotate it whilst it's measuring the field in all possible directions, and you measure the maximum and minimum in each field. In this way, you can find that hard iron vector that I told you that was shifting our sphere from being centered on 0, 0 to somewhere else. And you can then use this experiment to find this vector and subtract it. So here you have the measured, like just showing Y and Z axis, and here was the 0, 0, and then once we correct and remove the hard iron effect, we can center the data in 0 again. And also important to say that the idea would be that ecologists perform this temperature experiment before going to field work, then on field work prior to tag deployment, which means prior to the bird flying away with your tag and you monitoring it, you do the rotations, and then you do the calculations in the office afterwards, of course. And then for the soft iron correction, what we do is we get the data from this rotating like experiment. And once it's hard iron corrected, what we do is first, we find the ellipsoid that fits that cloud of points that are our measurements the best. And then second, we find the matrix that we can use to transform that ellipsoid into a sphere centered at 0, 0. And that's what happens here. You can see in green, sorry. In gray, it's the just hard iron effect corrected. It's centered in 0, 0, but you can see that's kind of squished in this direction here. Whilst the yellow one is the finally like corrected data, hard and soft iron, so like closer to a perfect sphere, it's centered at 0, 0. Yay, all good in that sense. Then the next step is what we call the magnitude correction. So basically what we do here is we look at the field measured by the tag in what we called arbitrary units, and we look at the standard deviation of the field as well. And then we go to the BGS website, the British Geologic Survey website, where they run an online geomagnetic model that can give you for any point on Earth the geomagnetic field and components, and it will be like 99 accurate for a calm day. So we go there and we check for the location where we performed the experiment, what was the expected field, and then we compare to what we had, what we found. So we found that the field was like 272.45 in arbitrary units, and when we the expected was like 50,154 nanotesla, which gives us a conversion or magnitude factor of like 184, whilst what you find as a default is 150. So it's important to do this correction to obtain the better accuracy in the data. Then what we did is like, okay, we perform all these calibrations and now we don't have a bird to put a tag on because we are in lockdown, Corona ruined our plans. What do we do? So the idea we had is like, okay, let's put one of these tags then on a kite, and we can fly it on a kite because we'll be kind of like a bird, right? I'm not a biologist or ecologist, so it's like, yeah, sure, we'll be like a bird. And from this experiment, what I can tell you is, one, it's much harder to fly a kite than you would expect, even when there is like a storm with like very strong winds, or I'm terrible at it. Either way, we flew the tag on this kite and we collected GPS data and magnetometer data. And then what we did is we used the coefficients we obtained on those experiments to then see if we could accurately retrieve the value of the geomagnetic field on the day we performed the experiment. In the same way an ecologist would do, like calibrate with all the procedures I told you in experiments, retrieve coefficients, and then like let the bird fly and just retrieve the data and correct it to see if we can get the accurate values. And what we found, luckily, is that at the scale of seconds, because the 3-axis magnetometer will measure like sometimes 3-4 times per second, depending on how you set it, we found an error between -4 and basically like 4 microtesla, but it's kind of almost centered around 0. However, you shouldn't really be using the measurements at the second resolution because it's really prone to noise due to all the facts I've told you already. So what we recommend is like using a moving average with temporal moving average in time to get the values at like minute resolution, and then it kind of starts to get better, and we see things of error between like 0.5 and -1.5, for example. As I told you, this like is still ongoing work, and we're trying to create these clear guidelines on how to calibrate the sensors and standardize the procedure so that we can then use this like data to understand the behavior of like these birds, and maybe finally be able to answer the question, do like birds and which birds use the geomagnetic field to navigate and how. And the idea from here is that we can start like comparing like birds migrating during quiet or stormy geomagnetic conditions and look at like how the heading distribution, tortuosity, physiological parameters, like what kind of change comes with changes in geomagnetic conditions like across years. Or particularly, we will be looking at high latitudes during migration because it's where you are more likely to have geomagnetic storms, really. Okay, so this was one case study, which is what I'm currently working on. And I think that fits pretty well in the idea, like if I have ancillary data, in this case about geomagnetic field, I can then try to understand behavior from a perspective where I can look at a variable and maybe in the future predict or know how a individual will react. Now more in the human mobility helm. This is a work that I did when I was working in Arizona. And basically the idea here, was that like you had bicycle commuting rising like 43% growth in the US from 2000 to 2017. And for that reason, you had many jurisdictions aiming to get data on like bicycling commuting and bicycling ridership. Because it becomes really hard to plan bicycling transportation if you don't have data on it. So the way that these local authorities found was basically to perform bike counts. And the way it can be done to get information on bicycling ridership is either manual counts, where you have counts across town and you have some poor soul sitting there for hours or the entire day counting it. And the other way is automatic counters, which you can perform counts every second, every minute of the day, but they are more like expensive to implement. And usually their spatial coverage is not so great because you have like just a few for a whole city. And with this idea of like having the counters and creating these counts, one question becomes very important. That's like, where do we place these counters? Where do we place these counters so that all our efforts, even if it's like placing someone to count there or investing in automatic counters, are used in the best way as possible? We get like a representative sample of biking ridership in our city. So thinking of that, the approach we decided to take in relation to it was like, okay, we have some crowdsourced data from like fitness apps, and maybe we can use like that because we have a better like spatial and temporal coverage. And it's known from research that crowdsourcing data created a lot of opportunities in different fields of like human mobility studies. So more specifically, what we did is we got data from the Strava fitness app. And I don't know if everyone here knows it, but basically you have the app that you can download on your phone and will track your like bicycle rides and sometimes your run if you want. And then you can see the trajectory in like many metrics. But the thing here is like when you are a user and you're looking at your own tracks, you see this pretty like trajectory that shows exactly where you were and where you went. But when we researchers, we get the data, we don't get this like pretty trajectory with all the information. What we actually get is the count of like bicyclists at a given minute of a year in each street segment of the geographic area we are working on. So here you have an example of the total ridership for San Francisco in 2017. We had like around 102,000 unique cyclists. And as if you don't know, I'm telling you now, Strava data is biased towards like male cyclists. So 77% of the users in this count were male. And the idea here was like, okay, we have had a lot of studies looking at different time steps of Strava data. So looking at its variation, the variation of the counts across seasons, across months, across years. But if we want to like use this information to know if we are representing all like possible patterns of bicycling ridership, we need to find a way to use Strava data to characterize bicycling ridership patterns in each street segment. So the idea we had was like, okay, so we will actually look at it in like, we will look at it in a way that we will create daily profiles for weekdays and weekends. And we will create this like curves with the volume of cyclists at each hour of the day, the average volume of bicyclists for each hour of the day for weekdays and for weekends. And then, okay, cool, I have like this curve now that show like some sort of profile, but you know, if I give it to urban, like someone working with transportation planning, like what they're going to do with it just looks like nice, you have cool curves. It doesn't give me any relevant information yet. So what we thought, like, okay, we need to find a way to actually measure the difference between these curves and then group them so that they make sense in terms of like transportation and ridership profiles and categories that we can link with to the literature. So the idea to do that, like, okay, we then use this, what we call a dynamic time warping, which is a technique from continuous signal processing. We use this to calculate the differences between the street segments in a way that, like, for each street segment, we created that like ridership profiles with the count for each hour of the day. So the first thing we do here is that we allow the warping in time of 1 hour before or 1 hour after the point being measured, so that we avoid, for example, comparing the first hour of the day for this street segment with the last hour of the day for this street segment, because that makes no sense. So we want to compare like maximum of 1 hour before or after in terms of profile. And this is the restriction shown by this yellow polygon here. So we count the difference between the cells and find the like least cost, the minimum cost path. And that is the dynamic time warping distance between one curve and the other. And with that, we then will create like this matrix where we have the total distance between each possible pair of street segments in whole San Francisco. And I think we had something like 33,000 street segments. Then once we do that, the idea is like, okay, we have the distance. Now it's easier to solve. We can apply some clustering technique and optimize it to find the best clustering solution. So that's what we did with hierarchical clustering. And we found the optimal number of clusters by using the Kalinsky-Harbaz index. And then once we found the solution of like the street segments that fit a given cluster, what we did is like we plot the average, the mean curves for each cluster. And then was the moment that we were kind of happy because like, well, this is kind of working actually. So you can see here an average profile of like medium morning use, low use utilitarian, high use mixed utilitarian. And of course, this didn't came like labeled, but we related the shapes here to the shapes in the literature. And here's just an example of like, when we map these categories back to that street segments in San Francisco, it's interesting to see that we have like some spatial contiguity like in the profiles, which makes sense. For example, we have like medium morning news in this area here that's like a green area in San Francisco. Here is another park. So it kind of makes sense, and we have like low use in connecting streets, for example. Then we like to validate these clusters. What we did is we create the same curves, but now from automatic counters that we had in San Francisco. And then we calculate the cross correlation between the curves that we had at those streets from Strava data and from automatic counters. And what we found is like for low use and medium morning use, we had an okay correlation. For like major roads, really bad. For mixed utilitarian, really good correlation, but like sample size, not great, because we had one automatic counter covering this type of ridership profile. So from the validation of clusters, the first thing we get, like, we would have to have more automatic counters in this category here, and we don't. So with these profiles, you can then like have an idea of like how many counters you should place in each type of street to create a more effective like counting program to have information so that you can plan bicycling ridership. I will skip the weekend profiles because we are running out of time. But the idea here is that once you have these profiles, even though we know they're biased because they come from Strava data, you can create target interventions. For example, if you know that a specific street segment or a group of street segment is more used by cyclists between 1 and 3 p.m., you can start creating things like a temporary exclusive cycling lane, so that cyclists will be happy because they will be safe and having their own space to cycle, but also like you will have a better flow of traffic in times where you have cars and you don't have so many cyclists, things like that. And then you can also think about like stratified sampling of bicycling ridership by placing your automatic or manual counters at specific locations, like strategically by ridership class, but also strategically in terms of like the time discounts are then happening. I think that's it for now. I talked a lot and I hope you enjoyed, and I'm open for questions now.
We've got questions.
Yeah, I
Right.
saw
So we've got
questions.
about 12 minutes for questions, and we have 8 questions showing in the Q&A, just so you have a sense of
It's
how
okay
many.
if I stop share.
Yeah, that'd be fantastic. Then everyone can see our faces. So just so you can sort of pace yourself, because it would be nice to get through these, but some of them I think sort of stick together in clusters of topics. But the first question is from Anita Grazer, who asks, how do you deal with representation bias in fitness app data? I'm sure lots of us are wondering about that.
Yeah, okay, so in this specific study, I didn't, because it wasn't the goal. But at the time when I was working in Arizona, we had another project working exactly with that. And the idea we came up, it's actually has been just, well, it's in press now, the paper. But basically we tried to create this generalizable, or as generalizable as possible, model to correct the bias for specific locations. And we use like a multivariate model that relates Strava counts and data from automatic counts, official counts, which is our ground truth, and variables that are known to relate to bicycling ridership, like distance to green areas or like density of primes, this kind of thing. And we tested it for different cities. We tested it for San Francisco, Tempe, in another 3 that I don't remember now because it has been 2 years since I did it. But the whole idea is that there are some variables that you can and should use for bias correction that don't change. They are consistent through cities. And there are other variables that will vary according to the type of city you have. For example, if you have a city that has like a seaside where you can bike, you must take that into consideration for that areas when correcting bias. But like if you don't have seaside, you have like green areas or other things that must be taken into consideration. So I think when you talk about crowdsourced data from fitness app, is still an ongoing challenge that some groups are trying to tackle. And our first approach was using a multivariate model and try to test it on different cities and see what's generalizable or not. So that's how we were trying to deal with it. I hope I answered.
I suppose the representation bias is not only sort of who's cycling, but whether you can extrapolate from this counts that you get in Strava to sort of what the total number of cyclists in the city is likely to be, right? But it's a really interesting question, because we know that some people are more likely to track their their movement than others. But if
Yeah.
you want a total count and where people are cycling.
Right.
Sort of,
Areas
it's a
are
really,
probably different.
yeah, it's a really interesting question. Okay, I'm going to move us ahead, even though I would really like to talk about representation bias. Victor Irakponor asks just a quick question about whether you use machine learning to predict movement and contexts.
Yes.
Very
Yes,
simple.
yes, we use different like techniques. For example, there is a paper I worked on looking at the weather and like how weather affect the movement of people in 5. And I used multi-channel sequence analysis and like optimal matching algorithms to calculate distance and look how the choices of like activities or transportation modes changed according to wind speed, rainfall, all sorts of things. So I kind of believe that you can do it without it, even if it's a tiny bit. You need it.
So I have Juan Tomas Sayago Gomez he has it as a comment, but I think it's a little bit of a question. Was really interested in why not use traffic cameras instead of counters or fitness apps.
That's actually an option, but then we go back to the same problem where you don't have the cameras everywhere. They are equipment that costs something, whilst with like the fitness app, assuming that you can get a deal with the provider, you can get it for free. And there are sources where you get, I agree that like some people say it's hard sometimes to get access to the data, but once you get, it's for free and you can get data every year. So you have like a consistent spatial coverage across years that you can like compare. Also, I wasn't doing, but like a Vipsa Roy, that's a PhD student, and she's a PhD student with Tristle Nelson. She has been working in some counts that were with like cameras, and then you add another layer of problem that's like how to extract the counts from these images. So there are always like pros and cons for each approach. I don't think there is a right approach. There is what will work for each authority according to their budget and like all other variables, but that's possible.
Yeah. So Anita Grazer has another question, which is, she asks, what are the most important movement context variables in your field of work? And this I think is an interesting part of the question. Which ones that are not used widely right now would you find most interesting?
In terms of like the most important movement context variables, that's a very hard one because it really varies with like the animal or like this kind of human mobility study. What I would say is that the most important in terms of movement context is to consider whether it can be represented by static or dynamic data. And that's the problem we often find, because you have often like static data representing dynamic context. For example, you have one land cover classification to represent the area in a study that spans like goes for 3-4 like years. That's not really the landscape changed in that period. So that kind of thing. And that are not used right now, I would find interesting, and that's one of the parts of my work, is that I really want to have more of like the remote sensed variables being used, but not only the ready to use products. Like I want to bring like the heavy go get your data and like make what you need, because then we get more options. We can use like multi-sensor approach data fusion and get more of the data we need. Of course, it might not be necessary in some cases, but sometimes it is, because we need dynamic representation and we don't have it because we don't have the ways to deal with the data, let's say.
Santiago Cardona asks if you were able to separate commutes and fitness travels in the Strava data.
When you get the Strava data, depending on the version, you get commute flags, but they are not like 100%. They are flagged by the users, but Strava also uses kind of an automatic algorithm that will flag it as a commuter or not. From the tests we did with the curves, yes, we can get it commutes from like, for example, leisure. That's very clear on the weekends that I didn't have time to show, but to really see a curve like with a peak in the morning and then in the afternoon for commutes, was for the areas around the, I think it's Golden Gate, the name, that's really nice view. You see more like a slow slope increasing, and in the middle of the day, this peak that's more typical of like leisure and like leisure cycling. Yes. So yes, it's possible.
Yanis Paraskevopoulos, I'm sure I just did a terrible job with your last name. I'm sorry, Yanis. Have you considered using or comparing network analysis methods, for example, space syntax regarding human mobility patterns?
No, I haven't yet, but maybe a good idea for a future project.
Fantastic. Santiago Cardona also asked, could you access Strava data for, so how did you get the data, the Strava data for the project at Arizona? And is it possible, I suppose, for anyone to do this? And is it from an API?
No, it's not from an API. You need to get in touch with the Strava team, the Strava Metro, and ask them for the data for like research purposes, and write kind of a short project and try to get a partnership. But they already have a dedicated like page for that. So I think it's easier than it used to be, but still it's not like freely available for many reasons, from like commercial rights to privacy. In Scotland, you can get data from UBDC in Glasgow. They have it for some cities I had in Scotland. I think Glasgow for sure. I don't know the others. But yeah, the UBDC is the Urban Big Data Center at Glasgow University.
Yeah. Another question from Anita Grazer. Is it sufficient to look at clusters by road class? And would you like to include any other spatial context information?
Great question. Yeah, well, I don't think it's sufficient, because I think we should consider other variables like POIs that you have in the areas and the street segments, and that's where I kind of paused on this work, because I started a new postdoc and I haven't had the time yet to finish. But basically the idea we had is we are still working on a project where we perform this cluster analysis. Then we use some methods to kind of look at how reliable these clusters are for each street segment. And then we create a like random forest classification that we can use to classify where we didn't have reliable or we didn't have reliable Strava data. And for that, we use other attributes like distance to specific POIs, to green spaces like population density, but I can't tell you much more because I haven't got results yet. But yes, it's important to consider other variables, and hopefully we'll have results on that soon.
So I have what I think must be almost a rhetorical question from Antonio Paez, who says only requiem or renewed life for Hagerstrand. And I don't know if you have a quick answer to that, and doesn't sound like an answer, like a question that has a quick answer.
Renewed life. I think I really like was like one of the things I really had to read when I started my PhD, because it's really connected to movement studies, and there are a set of papers that focus on how movement analytics is then able to revisit these questions that were posed by Hagerstrand, but with new tools. So that's very exciting. So yes, new life, I would say.
All right, so we're at the top of the hour, and I want to give Levi a chance to announce next week's talk. So I know I didn't get to all of the questions, but I think I'm sure if you had questions that were outstanding, you can always email Vanessa. And with that, I turn it over to Levi.
Yes, so thanks again for the great presentation, Vanessa. So this is obviously a talk series. Next week, we'll have sort of a double-barreled presentation with Professor Raquel Ortega Arguelles from the University of Birmingham and Dr. Emmanuel Tranos from the University of Bristol and the Alan Turing Institute, talking about the digital economy and regional inequalities in the UK. It'll be at the same time, 4 p.m. London, and the same registration on Eventbrite held through Zoom. In addition, all of the recordings will be made available on our YouTube channel, and this one will hopefully get posted within within the day or so. And let me pop that into the chat here.
Thank you. We're already getting questions on Twitter about the YouTube channel.
So yeah, so thank you very much. Hope to see you
right.
next week for digital economy and regional inequalities in the UK, and maybe later on for further sad talks. Thanks so much.
All right. Thanks, everyone. Bye. Thank you, Vanessa. That was fantastic.
Thank you. Bye.